discuss initialization in Gaussian integers. Oh, first of all, the quiz is not marked yet. It will be marked by Thursday. So I'm going to get the quiz there on Thursday. And the last Thursday we discussed something which is not really relevant to the course. Well, I mean, it is relevant to the course. It had to do with quadratic residues, but it was just some small part of thing, small thing which was kind of fun and short, and I just wanted to tell it in 20 minutes. But in the general, well, the thing that we actually discussed from the course material was Gaussian integers. We did it last Tuesday, and we discussed a proof of the fact that in Gaussian integers you do have unique factorization to prime numbers. So if you recall, the prime number is just a number which is not divisible by anything but units and units in itself. And we discussed the following. Every Gaussian integer can be factored in a unique way as a product of the powers of distinct primes. And this in a unique way means, well, yes, it's not really a unique way. It's up to reordering of the factors and up to multiplying each of the factors by a unit, and maybe even by, well, you can always multiply stuff by units because you can also divide stuff by units. So the units, even they always create some ambiguity, but otherwise units and reordering are the only sources of ambiguity. So you can always tell what is the largest power of a given prime that divides a given number. Something like this. And well, what I want you to do today is discuss the following thing. Well, we have usual integers, also Gaussian integers. So they should be factorable as products of some Gaussian primes. What is a Gaussian prime factors of a usual integer n? So the first question for today is like this. Given integer m factor is a product of Gaussian primes. So let's first of all make sure that it's really not completely trivial question. Say 5, well, it's a natural number. Moreover, it is actually a prime natural number. There are no natural numbers which divide 5. But in Gaussian integers, the claim it is actually not prime. It is composite. Does anyone see a way to factor this number 5? Yes. So 5 is 2 plus I times 2 minus I. Sorry? Yes, it's 2 squared plus 1 squared. Okay, so this number, even though it's usual prime, in Gaussian integers it's not a prime, it's a product of two different numbers, and each of those numbers is a Gaussian prime. Why is each one of those Gaussian prime? Sorry? Well, that's the definition, but why don't they carry factors about units and units times these numbers? Yes, the norm is 5. So these are Gaussian primes. Norm 5. And of course, if the normal Gaussian integer is a usual prime, 5, then this Gaussian integer is a Gaussian prime. The reason is, well, norm is multiplicative. If you can write this as a product of something with something, then the norm of this number 5 should be a product of two norms. But of course it isn't a product of two norms, well, besides 5 and 1. So these are indeed Gaussian primes, and they are really distinct. There is no way to take one of them and multiply it, well, by a unit to get the other one. If you take this number 2 plus I, you multiply by units, which are 1 minus 1 I minus I, you get only numbers which are different from this number. So that's factorization. Another example, 2. 2 is a usual number, it is a prime number. So it doesn't factor in Gaussian integers. Oh, yes, it is 1 plus I times 1 minus I. But that's not really the factorization that we want. The reason is because, well, first of all, these are Gaussian primes. They have norm 2, each one of them has norm 2, so they are Gaussian primes. Gaussian primes. 2. But in this case, they are not really distinct. If you take 1 minus I, or say 1 plus I, it is in fact 1 minus I times I. So you can rewrite this as I times 1 minus plus minus I squared. Yes. So like this. So they are not really distinct primes. They are the same prime. Well, in usual integers it would have been up to a sign, and here it is up to a unit. The unit is I. So then the factorization. 2 is a square in these numbers. Well, up to a unit. Well, of course, if you have some integer like this, then it's very easy to factor it as a product of Gaussian primes. You can first factor it as a product of usual primes, and then factor each one of these primes as a product of Gaussian primes. So it's 2 minus I, 2 plus I, times I, times 1 minus I squared. And finally, there are some integers like 7, which are really Gaussian primes. They're not only usual primes, they're Gaussian primes. What is the reason? Why this integer is not a product of any two Gaussian numbers, which are not non-units. Well, let's think about it. What is the normal set? $49. Yes, 7 squared plus 0 squared, so it is 49. If 7 is a product of, if z divides 7, z is some Gaussian integer, and z is not a unit, and not unit of 7, unit u, then what would be the normal set? Well, norm of a factor divides the norm of the number, because norm is multiplicative. So what are all the possible factors of 49? 1, 7, 49. But 1 is not good because it will be a unit. 49 is not good because, well, if some number of norm 49 divides z, then you divide 49 by z, or 7 by z, you get the number of norm 1. So you get the unit. So norm of z would only possibly be 7. But what is norm of z? If z is a plus ib, then norm of z is a squared plus b squared. Would it possibly be 7? Well, we can just check. That's very easy. 0 squared plus 7, well, 7 is not a square. 1 squared plus 6, 6 is not a square. 2 squared plus 3. Once again, 3 is not a square, and 4 squared is too large, so 7 is not a squared plus b squared for any integer numbers a and b. So this number is a Gaussian prime. It's a usual prime, and it is also a Gaussian prime, which is, as you see, stronger.
But why this argument doesn't work for 5?
Well, 5. What is the norm of 5? Let's just go over the same argument and try instead of 7, 5. Norm of 5 is 25.
Yes.
So if some number divides 5, then the norm of this number is 5. Well, if this number is a plus ib, then a squared plus b squared is equal to 5.
Yeah.
But 5 is 2 squared plus 1 squared.
Yeah.
So it has to do with the fact that 5 is a sum of 2 squares, but 7 isn't.
So that's when we have to check a squared plus b squared equals some number, we can get a pair of exponents. So if not, that is just like 7.
Yes.
But it's like no general.
Well, let's try to do it in general. So, indeed, these examples, well, I am in fact very genuine. You can generalize each one of those examples and get a general answer. Is, well, how to factor a given integer n as a product of Gaussian primes. So, let's try it more generally. Well, first of all, if we take an integer, we can factor it as a product of usual primes. That's the first step. And well, once it is factored as a product of usual primes, we can try to factor each one of those primes. So, to factor n is product of Gaussian primes. First factor is a product of usual primes. And then factor each of these primes. That's the lesson that we learned from this example. To factor 10 is a product of Gaussian primes, we factor it as a product of usual primes, and then we factor each one of these primes as a product of Gaussian primes. So now let's start with a prime number and see whether it remains a prime number in Gaussian integers, whether we can factor it further or not. So in this example, the reason that this number was not factorable as a product, well, was because this number 7 was not a sum of 2 squares. And we know, well, we know that which prime numbers are sums of 2 squares. We discussed it last time. Maybe let's repeat it a little bit. So if b is congruent to 3 modulo 4, then b is a Gaussian prime. So if b is 3 modulo 4 and b is usual prime, then b is a Gaussian prime. Let's prove this. Well, basically it's the same proof as what we did for 7. So the proof is if z is a divisor of p and z is not a unit and not a unit times p, then norm of z is a divisor of norm of p, which is p squared, and p is not equal to 1 and not equal to p squared. Hence the norm of z is p. Hence norm of z is p. If z is a plus ib, then a squared plus b squared is equal to p. But this means that a squared plus b squared is congruent to 3 modulo 4. But that's impossible. very simple argument shows that every usual prime which is congruent to 3 modulo 4 is in fact Gaussian primes. Is in fact Gaussian prime. It cannot be factored even in Gaussian integers. And the reason, once again, if there is a number which is a divisor of P, then its norm would be equal to P, because well, it doesn't have that many choices. It could be 1, P squared, or P. But it can be 1, because it would be unit. It can be P squared, because then the norm of P divided by this Z will be equal to 1, so P divided by Z would be unit. So it has to be P. But P is just not the norm of any number. It's not a sum of two squares, because it's congruent to 3 modulo 4. And here it's just because, well, a square is always either 0 or 1 modulo 4. So the sum of two squares would be 0, 1, or 2 modulo 4, never 3. So is this argument clear? Yeah.
This is an argument the other way around. If it's P is congruent to 3, 1, 4, then it's a Gaussian prime. Because here you started off with it's not a Gaussian prime, and then well, did you prove the contra?
Well, so I proved, so if some number divides this P and this not a unit, then well, it's impossible.
Or it's a contradiction of it.
Yes. So maybe it's better to say.
Is this a biconditional or just a condition? Like, does the proof for both? Is it taken only or just this?
So what holds, well, if and only if a usual prime is also a Gaussian prime, then it is congruent to 3 modulo 4. But we didn't prove this yet. You show that the next step will be to show that if it is congruent to 1 modulo 4, then it is not a Gaussian prime. And that is the other direction. So indeed, the next natural question is what happens if P is congruent to 1 modulo 4? So if P is congruent to 1 modulo 4, then P is Z times the conjugate some Gaussian prime Z. So I claim that any prime which is not of this form, well, there is also the prime 2, which is kind of special one. It's neither 1 nor 3 modulo 4, but well, most of the primes, almost all the primes are either 3 or 1 modulo 4. So those numbers stay prime even Gaussian integers. These numbers, well, they are always factorable as a product of exactly 2 primes. So it's always the prime number Z times the prime number Z conjugate. Well, let's see a proof. And essentially it is, well, last time we showed that any prime which is 1 modulo 4 is a sum of two squares. It's a squared plus b squared. So it can be factored a plus ib times a minus ib. Essentially that's the idea of the proof. But maybe let's try to repeat the arguments legally, because well, it was a legal mode, we would have forgotten them, and the arguments are pretty beautiful here. So assume to the contrary that P is a Gaussian prime. Assume, well, maybe first like this. If P is congruent to 1 modulo 4, then I claim that P is the divisor of some number of the form n squared plus 1. The reason is as follows. If P is congruent to 1 modulo 4, then minus 1 is a square modulo P. It means that minus 1 is a square modulo P. So it seems to be kind of an related fact, but no, it is in fact very, very much related. And then P is a divisor of a number n squared plus 1. So P is a divisor of some number n squared plus 1. Well, in usual integers, n squared plus 1 divided by P is an usual integer. In particular, this calls them Gaussian integers. But now look, if E is a Gaussian prime, so assume to the contrary that it is actually a Gaussian prime, then it means that, well, and P is the divisor of this product n plus I times n minus I. This number n squared plus 1 is factorable in Gaussian integers. It's n plus I times n minus I. So if a prime number divides a product, it divides one of the factors. So then P is actually a divisor of either n plus I or n minus I. P is the divisor of n plus I or P is the divisor of n minus I. But that's not possible. How is it possible that n plus I divided by P would be a Gaussian integer? Well, because it's not possible. But n plus or minus I divided by P, there are numbers like this. It's n over P plus minus 1 over P times I. Definitely this coefficient is not an integer. It's 1 over P. So it's not a Gaussian integer. So that's a contradiction. So the conclusion is P is not a Gaussian prime. Well, so for now we just know that it's not a Gaussian prime, but we want to actually factor it as a product of Gaussian primes. So hence there exists Z which is not a union, but not union times P. Which is the divisor of P. Now I want to conclude that actually P is a product, Z times Z conjugate. Does anyone see how to show that P is actually a product of Z and its conjugate?
P can be written as a power square.
Well, now we have a simple way. Okay, yes. So normal Z which is indeed Z and Z conjugate. This number is the divisor of, normal P, which is P squared. But that's a usual integer. So maybe for now just say that norm is a divisor of P squared, but it is not equal to 1 and it's not equal to P squared. Because it's a non-trivial factorization. Z is a non-trivial factor of P. So hence, normal Z is equal to P. But normal Z is exactly Z and Z conjugate. So hence, P is Z times Z conjugate. Well, and of course, if Z is prime, Z conjugate is also a prime. Because, well, if you have factorization of Z conjugate, just conjugate it and you get factorization of Z. So Z and Z conjugate, well, the factorizations are related to each other. One is the conjugate of the other. One of them is prime, the other is a prime. Well, we still have to check a little bit. Z and Z conjugate are actually distinct primes, even after units. So one can check. Z is not a union of Z conjugate. So in fact, for any prime which is 1 modulo 4, we have a factorization like this. In Gaussian integers, such a prime is a product of two Gaussian primes. And these Gaussian primes are conjugates of each other. Question? Okay, so once again, we once again reprove that such a prime number is a sum of two squares, because this prime number is normal something. And this time we went a little bit further. We showed that P can be factored as, well, in Gaussian integers in this way, z and z conjugate, for some Gaussian prime z. And finally there is the prime 2, which, well, is neither in this category or in the other category. It's neither 1 modulo 4, it's not 3 modulo 4, but that's of course easy. So let's formulate this as a theorem. If a prime is equal to 2, this prime is in fact I times 1 plus I, 1 minus I squared. So 2 is the square of some prime in Gaussian integers. If P is congruent to 1 modulo 4, then P is z and z conjugate of some integers, and that the conjugate is actually distinct prime, is distinct from z. It's not equal to z even after units. And finally, if P is congruent to 3 modulo 4, then P is just P. It is prime itself. So the theorem tells you how to factor any usual integer n as a product of Gaussian primes. Factor it as a product of usual primes, and then factor each one of those primes using this table. So maybe any questions about this theorem? So let me use this theorem to count the following interesting numbers. How many integer points are there on the circle, on a given circle? So the question is like this. You have your plane, you mark the points with integer coordinates. You fix some number n, and you ask how many integer points are there on such a circle. So for example, you fix the number n to be equal to 2, and you draw a circle whose radius is square root of 2. And well, here you get 4 points. And the question is, well, in general, given a number n, how many integer points are there? Or, well, in other words, how many Gaussian integers are there whose norm is equal exactly to n? So, question. How many integer points xy are there on the circle? x squared plus y squared is equal to n, equivalent to how many Gaussian integers of n. So it's the same question. How many Gaussian integers other whose number is equal to n? Or, once again, how many ways are there to write n as a sum of two squares? So you see, it's a rather natural question, either from geometric point of view, or from point of view of Gaussian integers, or even from usual non-theoretical way of seeing things. It's an interesting question. We fix a number n, how many ways can be written as a sum of two squares? How many integer points are there on such a circle? Very natural questions. And now we have a very simple way to answer this question. Well, we want answer, write solution. I want to write my number n as a norm of some. Well, I want number Gaussian integer z such that norm of this number z is equal to n. So I want to write n as a product z and z constant. Well, I want to write n as a product of something, and I do know how to write n as a product of prime factors. So n, let me write it as a product of Gaussian primes. What is it? Well, I might have a unit, then I have the prime number. Well, n is a product, first of all, well, let me say it like this. Let me keep it positive. So, n is a product of usual primes. It's 2 to some power times the product of some primes k1 to k1 times, and so the n, sorry, os to k to this k. And let me separate the primes which are congruent to 1 modulo 4 from those which are congruent to minus 1 modulo 4, because I know that they behave differently in Gaussian primes. So let me write this like this, q1 to r1 times qm to rm. And the explanation here is like this, pi is congruent to 1 modulo 4, ui is congruent to 3 modulo 4. And they are primes. So I would like to write n as a product of Gaussian primes. First step, let me write it as a product of usual primes. In this factorization, let me separate the primes which behave differently in Gaussian integers. 2 behaves in somewhat exceptional way. The primes which are congruent to 1 modulo 4 behave in one way, and those which are congruent to 3 modulo 4 behave in somewhat different way. So now let me write the factorization of n as a product of Gaussian primes. So in Gaussian integers, have the following factorization. So 2 is I to some power times 1 plus I to the power of 2 times t. Each one of these numbers can be factored as a product of some prime z times its conjugate. So it's like this. z1 to to the power s1 times z1 conjugate to the power s1 times and so on times zk to the power sk zk conjugate to the power sk. So this is p1 to the power s1, this is pk. Well, I use Z, but not Z1, Z2. So I guess it's okay. Well, and finally, I still have these primes. But these primes are still primes in Gaussian integers. So I can continue times, P1 to the power R1, and so on, times 2n power Rn. So this is a factorization to Gaussian primes. And now I want to write this number as Z and Z conjugate. Well, Z and Z conjugate are both Gaussian integers. So they must, well, be composed somehow of Gaussian primes, and in fact of these very primes, the ones which already appear here, because their product is equal to M. So let's try. I want Z and Z conjugate to be equal to this number. So I want such quality to hold. So I want to decide how many times different primes that appear here divide Z. Well, let me try. I'll try to write the factorization of Z and Z prime to prime powers. Let's see. I want, here's one prime, 1 plus I. To what power should it appear in Z so that in the product it will appear 2t times? Yes, so in fact it can be right. So take Z and write it as 1 plus I to some power. Well, for now this power is unknown, but then I know that Z conjugate has this prime factor, well, has slightly different prime factor, 1 minus I to the same power. And then the product Z and Z conjugate has 1 plus I times 1 minus I to this power. But 1 minus I is in fact, well, after I, the same thing. So in the product, the sum of this number and that number is exactly 2t. So each one of these numbers must be equal to t. But that's the only way it can work. So first of all, it does work. Z and Z conjugate will have 1 plus I to the power t times 1 minus I to the power t. So it's 2 to the power t, or I to the power t times 1 plus I to the power 2t. And in fact, that's the only way it can work. If there is some power here, there is the same power here. And the sum of these two powers should be equal to 2t.
Okay, let's see if I say like 1, if that equals 1 plus I to t, and then conjugate is like I minus 1 to t. Even though these have something together, it's all the same, like 2. Or like, depends on t's operator.
Well, here the exponent is even automatically, it's 2 times t. So it must be unequal parts between z and z conjugate. So there is t powers here.
explain how that the conjugate 1 minus I related to 1 plus I?
Okay, so let me write it a little bit more, a little bit more details. So if Z is 1 plus I, the sum power what number 10 cubed? Sum power T is 8. Suppose it is 1 plus I to the power I, 8 times some W, and W is relatively frank to 1 plus I. So suppose I factor the largest possible power of 1 plus I out of the number Z. Then Z conjugate is 1 minus I to the power A times W conjugate. And this is the largest power of 1 minus I, which I can factor out because the CD of W conjugate to 1 minus I is still 1. So just conjugating this equality. And then Z and Z conjugate is 1 minus I to the power A, 1 plus I to the power A times W conjugate. So the prime number 1 plus I does not appear in the factorization of this thing. So I can write it as I to the power A, 1 plus minus I. Plus I minus I to the power 2A W. Yeah.
Should the factorization be 1 minus I to the 2t?
1 should be 1 minus I. But once again, it's all the same. I mean, even if it's plus I, then instead I can write minus I here. So let's correct it here. So you see that then the power of 1 minus I that appears here is 2A. If I want this power to be equal to 2t, I must have A equal to t. So hence A must be equal to t. I must split this prime factor, 1 minus I to the power 2t, in equal parts between Z and Z over conjugate. So we managed to understand how one of these prime factors splits. Let's try other prime factors. So get the factorization here. So here, once again, I have this factorization. Well, let's see. What power of Z1 could possibly divide Z? Well, it should be some power. So let me start by doing like this. Z is Z1 to some power and 1 times other stuff. Other stuff means product of primes which are not equal to Z1. Then we have the Z conjugate is Z1 conjugate to the power n1 times other primes. But then I also know that yes, so let me look at this. Z1 to the power n1 times Z1 conjugate to the power I still need more letters. z1 to the power m1 times order to the power primes. But in the product z and z conjugate, I have then z1 conjugate to the power m1 plus m1 and z1 to the power m1 plus m1 and times other primes. So the only condition that I really care about is that m1 plus m1 is equal to s1. So m1 plus m1 should be equal to s1. So I can choose any number n1 from 0 to s1, and then choose m1 to be s1 minus this number. Yes.
Where did the Q come in?
So Q's are the primes which are congruent to 3 modulo 4, and then they are still primes, the remaining primes even Gaussian integers.
Or is like separated like more simply like z equals to z1 to zk and I z conjugate is like z conjugate.
Again,
Okay,
Z is
z1 to zk, like to s1 actually. Just to s1. And we'll separate to the 1.
It's like put all the unconjugated one and then conjugated version in the other.
well, either way, you're going to get the same result. That's all.
I just want to point out that that would give one factorization, like we're always writing it as z and z conjugate.
Yes. So we are looking for always, and we are trying to figure out what are the possible exponents here, m1 and m1. And we figured out that in all possible factorizations, the only thing that actually matters is that m1 plus m1 is equal to s1.
So just
Once it is satisfied, we do get factorization, though at least as far as the factor is z1 somehow is concerned. Okay. Well, of course, it didn't matter that this is z1 and not z2, z3 or any of those. So the same story with each one of these. So I can change the index 1 here to index I. Still. Still, the only thing that matters about the exponents of Zi, which is in the factorization of Z, is that Ni plus Mi here is equal to Si. And finally, what happens to these factors of Q? We call that Q is a usual prime. Qi are usual primes. So if Z is Qi to some power Ni times something, Z conjugate is Qi to the power, well, Qi conjugate to power Ni times something. But these are real numbers. They're actually usual natural numbers. So the same as Qi to power Ni times other stuff. So in Z and Z conjugate, we have Qi to the power 2 times Ni times and so on. So the power, so the condition is like this. The power of Q which divides N, which was called Ri, must be equal to 2 times Ni. They have to be even. Otherwise, there is just no factorization. Now we have kind of answer. Oh, a complete answer.
So if Ri is I, then the original integer is
It's
just
not-
a Gaussian prime.
Yes, no, it's not a Gaussian prime, it's just not a norm.
It's not a norm.
Oh,
Sure, that's true.
No, it's still not a Gaussian prime, but it's not a norm.
Okay.
So now let's formulate an answer. If n is t to the power t times p1 to the power s1 times t a is t times q1 r1 times First consideration, if one of these numbers is odd, then this number n is not a normal thing. So if Ri is odd, some I, and n is not a number. It's not a number. It cannot be written as a factor of z and z function. Otherwise, we can write n z and z conjugate in how many ways? Well, we should split these powers of the primes somehow between z and z conjugate. And we decided that these 2 to the power t factors as 1 plus I to the power 2t, and this 1 plus I to the power 2t must split in equal parts between z and z conjugate. No choice here. Same about these kind of primes. They must split in equal parts between z and z conjugate. So no choice here. But for each one of these primes, we can factor it as zi to the power equal to some power times zi conjugate to the same power. And here we can make a splitting, we do have a choice. Essentially, we can make a choice of any integer, ni, between 0 and si. And then we have factorization matrix. Once you have ni, you know what mi is, and there are no further choices. So essentially, we can choose just the following things. We can choose the powers from 0 to s1, from 0 to sk, well, in the way that this prime factors split between z and z conjugate. So we get s1 plus 1, that's the number of choices for splitting z1 to power s1 times z1 conjugate to power s1 times and so on is a plus 1. And that's the complete answer. So given an integer, we just know in how many ways you can write it as a norm of something, and how many ways you can write it as sum of 2 positive squares or 1 negative squares. That's the answer. Factor it as a product of usual primes. Well, of those primes, distinguish those which are congruent to 1 modulo 4. Write down what are the powers of these primes which appear in the factorization. So write down this number, that's the answer. Example, if n is, say, usual prime which is congruent to 1 modulo 4, there are, according to this formula, 1 plus 1 ways. So exactly 2 ways. For example, so this theorem, well, it shows us not only that we can factor such a prime number. We can write down such a prime number as the sum of two squares, but essentially we can do it uniquely. And more generally, if you have any number, you can decide in how many ways you can write it as sum of two squares. So maybe let me formulate answer to another question, number of integer points on such a circle is, well, it's essentially this number, but here, well, here I wanted to write it as sum of two So here I'm not counting the ways of plus minus 2 and plus minus 1, and here I'm only writing it for, well, up to units. So I can always multiply z by a unit and z conjugate by the conjugate of this unit. So essentially, here I'm counting only ways which are not equivalent up to units. If you do count, including the difference with the units, which means, well, here you count not only points in one quadrant, you count all the points, then you get 4 times s1 plus 1 times s2 plus 1. Okay, so maybe let's make 10 minutes break, and then we'll play with this formula tomorrow.